All right, so now we'll study a phenomenon. Okay, so here is a solid object. Its temperature is T. If you heat it, if you raise its temperature, you see its dimension increases. So it's the length of this object increases by that much. What happened was when you added heat, when you raised its temperature, you added heat. And here's a model for the solid. Here are the atoms of the solid. And you can think of them as attached by springs. That is modeling the intermolecular forces. And the spring expanded, and you added potential energy, and these molecules moved further away. Every molecule moved further away, and the the solid expanded. Now let me show you how much the solid will expand. Okay, so this table shows you the number. So iron or steel, what it expands is, if you raise the temperature of steel bar by 1 degree Celsius, what this number is telling you, it'll expand 12 parts in a million. That's what it's telling you. Okay. So let's go to the blackboard. Oops. Let me add a page. Okay, so if you had an iron rod that was 1 meter long, you raise its temperature by 1 degree Celsius, it expands by 12 times 10 to the minus 6 meters. Okay, or 12 times 10 minus 3 millimeters. 0.012 millimeters. Okay. Now, so you wonder, why the heck do we care if it expands by that little amount? Okay, 1 part in 100,000. That's what it amounts to. Okay, so that's what we are studying. Okay, so here's an object, you raised its temperature and it expanded. Okay, so here's where it comes into play. Okay, so here's a bridge in Michigan, and it's a kilometer long. Okay, so it has a length, the center span of the Mackinac Bridge in Michigan has so this is the center span, has a expansion gap, has a length of 1 kilometer, 1.1 kilometer. And it sees a temperature change of 100 degrees Celsius over a year. So from the dead of the winter to the heart of the summer, it will see a temperature change of 100 degrees Celsius. And this bridge, the center span, would expand by 1.5 meters when it sees this length. When it sees that temperature change, it'll expand by 1.5 meters. Okay. And so if the length increased, so that would, you see, this rod would bend. Okay. What this is a bimetallic strip, and this thing bent because, again, this thing bent because there are two different metals and so on. But in this bridge, if you didn't accommodate for the expansion, length expansion, this bridge would buckle. And the way you accommodate for that is you leave expansion, thermal expansion gaps like that. So you see, and you've seen this kind of stuff on every bridge has these. Okay. So these are gaps that are left between spans. So this is a picture taken in the winter, and here's a picture taken in the summer when the bridges have expanded. And if you do not leave these thermal expansion gaps, these structures like these would buckle. Okay. So here's another picture of thermal expansion gaps. Okay. Okay. So that's what we are interested in. Okay, so as an engineer, you'll have to solve problems like that. Okay. The increase in length of this object is the length of the object times the rise in temperature times the coefficient of linear expansion, alpha, the coefficient of linear expansion, which is alpha is given here. So for steel, it's 12. And interestingly, for concrete, it's also 12 times 10 to the minus 6 per degree Celsius. Okay. For aluminum, it's about twice as much, 25 times 10 to the minus 6 degrees per Celsius. This is the coefficient of volume expansion. We'll come to that in a second. And you can see that for most materials, the volume expansion coefficient is 3 times the linear expansion coefficient. Okay. Okay, so those are thermal expansion gaps that you have to leave for structures to be able to expand. You see those cuts on sidewalks as well, and those are thermal expansion gaps as well. Okay. All right. So here's another bimetallic strip in application. A bimetallic strip is made of two strips of metal of different material. Okay. And so what's happening here is when you heat this, see the thermal expansion coefficient of B is greater than A, and so it bends upward. And you can think of a thermostat being built this way. This, when it's straight, it's in electrical contact, and when the temperature rises too much, the electrical contact is broken, and you can imagine that the heater is being turned off. Okay. So here is the electrical contact. You turn on the heat, and when the room gets too warm, this thing bends upward, the electrical contact is removed, and the heater is turned off. Okay. So between rail tracks, there are thermal expansion gaps, and you see this is the result when not enough of a thermal expansion gap was provided. The track buckled, and of course the train wouldn't want to go on that. The Trans-Siberian line is 10,000 kilometers. So that's that's in Russia, and that's 10,000 kilometers, and it sees a temperature in the dead of the winter. The temperature is can get to minus 31 degrees Celsius, and in the summer 35 degrees Celsius. So it can see a change of 66 degrees Celsius, and the gaps between the rails add up to 8 kilometers. Okay. So anyway, so you have to be careful of all of that. Okay. What this shows you is area expansion. So for instance, here's a washer. And now the question is, so here's a metal washer. You heat it, and the metal washer gets bigger. And the question is, how does this gap expand? And what this diagram is showing you is, so imagine this gap filled by the same metal, and as this heats up, if it was filled with metal, it would expand as if it was made, well, the metal would expand. So if there was a gap, the gap would expand as if it was made of the surrounding material. Okay. So the gap expands exactly as the material itself. And by the way, the area increases 2 alpha times area times the rise in temperature. Okay, so the area expansion coefficient is just twice the linear expansion coefficient. Okay. And so here's an engineering application. Let's say you want to make a ball socket joint. If you want to make a nice ball socket joint where the ball would not come out, you make the socket gap is smaller than the diameter of the ball. And to make the joint, you heat up the socket, pass the ball through it, and once the socket cools, you have your joint. Here's the volume expansion coefficient. Just like the area expansion coefficient, the volume, the gap expands just like it's made out of the solid. Okay. So the volume expansion coefficient is beta times the volume of the material times the rise in temperature. And beta, the volume expansion coefficient, is 3 times alpha, the linear expansion coefficient. Here's an interesting graph. All right, let's go to the chalkboard. Okay, so here's a substance. Now for most materials, if you raise the temperature, it would expand. The density is the mass divided by volume. Since the volume increased, the density would decrease. So for most materials, you raise the temperature, the volume increases, and the density decreases. All right, let's look at this graph. So here's the density of fresh water. So this is for water. And this happens in only a very small window. Okay. So in the window 0 to 4 degrees Celsius, you're raising the temperature and you see the density is increasing. Outside this window, water behaves normally. If you raise the temperature, the density is decreasing, just like any other material. But in this small window, it's behaving differently. So you're raising the temperature and the density is increasing. And this is a phenomenon that's only 1 part in 10,000, but it's extremely important. Okay. So let's see what this does. Okay. So this is extremely important to life. So for instance, let's say you had a lake and you wanted to freeze this lake. Okay. Now this lake was at 10 degrees Celsius, the water was at 10 degrees Celsius, and you want to freeze this lake. What you do is, if you want to freeze this lake, what you do is you make the air real cold. And you are all experts in thermodynamics, and you'll know that heat will flow from a hotter object to a colder object. Okay, so that's what you do. So now heat is flowing and the temperature drops. So let's say the water is cooled down to 4 degrees Celsius, and you saw from our graph at 4 degrees Celsius the water is densest. Okay, so that's the important point. At 4 degrees Celsius the water is densest. So it cooled down to 4 degrees Celsius, and the denser the material, it settles to the bottom. So this became 4 degrees Celsius. So eventually the whole lake was 4 degrees Celsius. And now heat is still flowing out. So now, let's say this is at 2 degrees Celsius. At 2 degrees Celsius. But now this water is less dense than this water, so it doesn't need to settle down. It won't settle down, so it'll remain there. And then eventually this will go to 1 degree Celsius and then to 0 degrees Celsius. And this water will freeze. Okay. Now this has become ice. Okay. And ice has its density, the density of ice is less than that of water, and it floats. Okay. So that's another phenomenon that was important. Okay, now we have a sheet of ice on top. Okay. The air temperature is still minus 20 degrees Celsius, but the thermal conductivity of ice is small, and so this is acting like a blanket. And so now the heat flow is decreased tremendously. Okay. And so even you can keep this temperature cold all winter long, and all we have done is we formed a layer of ice, and this is still water. Okay. And life can survive in this water through the winter. So we have to thank this curve for the fact that the entire lake doesn't freeze, and so that's important, and that's important for life. Okay. Anyway, so 1 in 10,000 phenomenon. Such small things can be important. All right, so now we'll define heat. Heat is, so here's a model of a solid. At any given temperature, these water molecules are vibrating, okay? So there's random kinetic energy and potential energy associated with every particle, Okay. So the internal energy is a sum of the random kinetic and potential energy of all the particles. Okay. And if this object is hotter than another object and it loses some heat, it transfers heat from this object to another object, what is happening is you're losing this internal kinetic, random kinetic and potential energy. That's what's being transferred. So internal energy or thermal energy of a system is the random internal kinetic and potential energy of the constituents of the system. Okay? So heat, when we say heat is transferred, it's the internal energy transferred between objects because of temperature difference between them. Okay, so that's what heat is. Okay, back in the old days, we didn't know what heat was. We thought it was some kind of fluid in an object. But once we realized heat is a form of energy, heat was measured, heat used to be measured in calories. Once we realized heat was a form of energy, how many calories is a joule, that conversion factor was important to find. And Mr. Joule found that, and that's why the unit of energy was named after Mr. Joule. And here was his instrument. Okay, so you can see that here's this string that goes over a pulley with the weight attached to it. And as the weight falls, it turns the paddle. So what you do is, so you drop the weight to a certain height, it turned the paddle, which warmed up the water, and you measure the rise in temperature in the water. Okay. And so what Mr. Joule did was the following. Okay, so when the object drops a certain height, its energy can be calculated. Its loss in energy was mgh, which can be calculated in joules. And when the water temperature rises, its energy increase can be calculated in terms of calories. Okay, so this is in calories. And this energy loss was converted to heat, and so this is equal to that. So this many joules is equal to that many calories. Okay? And that's how Mr. Joule found the conversion. Okay? And 1 calorie is 4.186 joules. Okay, so let's fix that. Yeah, okay, anyway, it's 4.186 joules. Okay. Okay, let's define specific heats. These are for solids and liquids. Okay. So here's a solid or liquid, and if you add heat to it, its temperature will rise. Okay. So when you add this much heat to an object, its temperature rises. Okay. The temperature rise will depend on how much mass you have. So the amount of heat added is the mass of the object times its specific heat times the rise in temperature. So the specific heat is added as, if this was 1 kg and the rise in temperature was 1 degree Celsius, the specific heat is the amount of heat added per unit mass per degree rise in temperature. Okay. The specific heat is amount of heat added per unit mass per degree rise in temperature. So the specific heat is heat added per unit mass per degree rise in temperature. So this is for solids and liquids, it's easier to measure their mass. When it comes to gases, it's easier to measure the number of moles. And so we define molar specific heats. How much heat you added per mole per degree rise in temperature. So for solids and gases, we do define specific heat differently. Okay, just is based on what's convenient to measure. So okay. And when we come to gases, we'll do another thing. So this is for solids and liquids. And for gases, it's molar specific heat. Q divided by N, the number of moles divided by that. And then we'll define specific heat at constant volume and specific heat at constant pressure. That is, we are adding heat at constant volume or constant pressure. And you'll see in the next chapter that Cp is always greater than Cv. What we're saying is you have to add more heat to raise the temperature, everything else being the same. If you want to raise the temperature by a given amount, specific heat, increase in specific heat at constant pressure is greater than specific heat at constant volume. Okay. All right, so here's how the specific heat is defined, and here are some specific heats for various substances. Water has a very high specific heat, 4,186 joules per kg per degree Kelvin. And you see, for most metals, the specific heat is about 1/10 of that of water. Land is about, land is essentially a lot of silicon dioxide. Land has a specific heat that is about 1/6 that of water. So you can see that. And so what this diagram is showing you is during the day, equal amounts of energy, sunlight is falling both on water and land. Land has a smaller specific heat, so its temperature will rise more. Land gets much warmer. The air above land gets warmer, it gets less dense, and it rises. The pressure is low here now. The pressure is high, and wind blows from a higher pressure to a lower pressure region. So during the day, you have a breeze blowing from the ocean toward the land. At night, since the heat content of land was lower, it cools faster. Water retains its heat much more, so the ocean is warmer, or the lake is warmer. And now this air rises. The pressure is lower here, and a breeze blows from here to there. So if you live close to a body of large body of water, you're always getting a breeze. And that's why that land is expensive. Okay, so now we'll talk about latent heat. Okay. So let's go to the chalkboard. Okay. Now, normally, you add heat to an object and its temperature will rise. Okay, and so that's what that formula gave you, the amount by which its temperature rose. But it turns out that if you do the following experiment, let's say you have, okay, so let's do the following experiment. So you take a bunch of ice, okay, and let's say this ice was at -5 degrees Celsius. So that's generally the temperature of your freezer. And you heat it. Okay, what you find is, so you're adding heat and you're measuring the temperature, -5 degrees Celsius. The temperature of the ice will rise up to 0 degrees Celsius. And then, even though you're adding heat, the temperature is not rising. Okay, so when this comes to 0 degrees Celsius, the temperature does not rise even though if you're adding heat. And what is happening is the ice is melting, phase change is happening. And during phase change, the temperature does not rise. Okay, so what is happening to all the heat that is going? you're not raising the temperature. So what is happening is, what you're doing is you're breaking the bonds, okay? So heat added, when latent heat is involved, does not raise the temperature of a substance. The energy is required to overcome intermolecular forces. So from a solid, um, when you go to a liquid, on the average, the separation is higher. And when you go from liquid to a gas phase, the separation is higher. So all the energy went into breaking the bonds, and that heat is called latent heat. So the heat did not increase the average kinetic energy uh, of the molecules, okay? And that is latent heat. So when a phase change happens, the amount of heat added is the mass converted from one phase to another, times the latent heat, okay? So you see, when when ice, when water melts, it melts at constant temperature. So all the heat added is going into the latent heat. And once you melted all the ice, then you can raise the temperature of the water. And similarly, when water boils, all the heat is going into converting water into vaporization. So you cannot raise the temperature over 100 degrees Celsius at 1 atmospheric pressure. Okay. Once you convert it into steam, in principle, you can raise the temperature of steam to anything you want. Okay. So your latent heat, so fusion meaning melting during phase change from solid to liquid, this is the amount of latent heat added. So you see water has a latent heat, a very high latent heat, 33.5 times 10 to the 4 joules per kg. And it's more than that of gold, for instance, and lead and so on. So gold and lead are easier to melt than water and then ice. Latent heat of vaporization, latent heat of vaporization in water is quite large as well, 22.6 times 10 to the 5 joules per kg. Much is higher than even for gold. So it's easier to vaporize gold, takes less energy to vaporize gold than water. All right, so we are thankful for this high number, okay? And here's the deal. Okay, so here's a thermodynamic system, here are thermodynamic systems. And if you go on a run, so even if these thermodynamic systems were just sitting and reading a book, so this guy was reading a book, he's producing 100 joules of heat per second. So a person's just sitting down is glowing like 100 or 150 watt bulb. Okay, you have to get rid of that heat, because if your body temperature rises by 1%, let's say your body temperature is 97.6 degrees Fahrenheit, if it rises to 97.6 degrees Fahrenheit, you have a fever. You don't feel good. And so you have to maintain your body temperature. Okay, and so our cooling systems are extremely efficient. Okay. So complex life forms operate optimally within a small temperature range. Humans work best around 37 degrees Celsius, which is about 100 degrees Fahrenheit. That's because reaction rates double every 10 degrees Celsius. What that means is, so here the so let's say these are potatoes and you're boiling potatoes. So, and the water boils at 100 degrees Celsius at 1 atmosphere. And so it takes 30 minutes to cook the potatoes. Okay. Now, what that reaction, let's say for instance, if you could boil the potatoes at 110 degrees Celsius, now they would only take 15 minutes to cook. Okay. If you could boil the potatoes at So, well, let's change these numbers. It says 60 minutes, 30 minutes. Okay. Now, if you could cook the potatoes at 120 degrees Celsius, then they would cook in only 15 minutes. Okay. So that's what we mean by reaction rates doubling every 10 degrees Celsius. Okay. So, but how do you make water boil at 120 degrees Celsius? Okay, so here's the trick. You put a lid on it, build up the pressure, and if the pressure in here is 2 atmospheres, at 2 atmospheres, at 1 atmosphere, water boils at 100 degrees Celsius. At 2 atmospheres, the water would boil at 120 degrees Celsius, and that's what a pressure cooker is. Okay, so the initial steam evaporating is trapped. You build the pressure up to 2 atmospheres, and now the water is boiling at 120 degrees Celsius, and things are cooking much faster. Okay. Anyway, so a human life form, there's millions of reactions going on inside the body, and they're all interdependent. So if arbitrarily you can't increase the reaction rate of one reaction because other reactions depend on its reaction rate. So that's why the human body wants to maintain its temperature constant at 37 degrees Celsius because it's a system where millions of reactions are going on simultaneously and they're interdependent. Okay, so now, so you have a system whose temperature you have to maintain constant. Okay, so here's this system, thermodynamic system. When it was just sitting down, it was glowing like 150 watt. It was producing 150 joules of heat per second, and you had to get rid of 150 joules of heat per second. Otherwise, you would heat up. And now if this system went for a run, now you're suddenly glowing like 1500 watt bulb. You're producing 1500 joules per second. Now you have to get rid of more heat per second. Okay. So the thing is, how does the system maintain its core temperature? That's the question. Okay. So that's the engineering question. So how do you remove the excess heat? So 130 pound, here are the numbers, 130 pound person generates 80 joules per second. By the way, 20% of the heat is generated in your brain. Yes, 20% of your energy consumption is in your brain. Such a person running would generate 1200 joules per second. So how do you remove this excess heat? So here's what the body does. Okay, so humans have sweat glands and you sweat. Okay, and just sweating doesn't do it. What you're hoping for is the sweat to evaporate. And when the sweat evaporates, for every gram of sweat that evaporates, it takes away 540 calories. Okay, and that's how you cool the system. Okay, so for instance, if you go to a doctor and get all your sweat glands removed, you would never be able to go for a run. Okay, or if you did go for a run, that would be your last run. Okay, so we have extremely efficient cooling systems. So it takes 1 calorie to raise the temperature 1 gram of water and 540 calories of heat to vaporize 1 gram of water. That is that number in different units. Okay, so the latent heat of vaporization. Okay, so when sweat evaporates, it removes heat from our bodies. Here's an amazing fact. Our cooling systems are extremely efficient. It is claimed that people can survive temperatures of 124 degrees Celsius long enough to cook a steak. Okay, so what this statement is claiming is, so you can go to Publix and buy a steak. Here's an oven. Here's the person. You can walk into a large oven with your steak, and the steak cooks, and you're able to walk out. Okay, so that's the claim. Now, I don't know if you still have an appetite to eat the steak, but nevertheless, you can walk out of the oven. So that's the statement. Absolutely amazing. So here's another amazing fact about this number, the latent heat of fusion, okay, which is a large number as well. These numbers are just illustrating how large amounts of energy is being moved in nature. Okay, so here is Lake Superior. This is, oops. So we'll talk about Lake Superior. It's about half the size of Florida, and 150 centimeter thick layer of ice can form on the lake. 150 centimeters is roughly the height of a person. Okay, so that's 5 feet. 150 centimeters is 5 feet. Anyway, so you're forming on Lake Superior. So here's Lake Superior. Okay, and you're in the winter. See, you made the air was cold, and a layer of ice forms over Lake Superior. Okay. And so this is 5 feet thick. Now, to freeze water, you have to remove a lot of heat from the lake, and heat flowed from the water lake to the cold air. Okay. So the question is, how much heat is this? Okay. And so let's look at the numbers. So it turns out to form that thickness of layer, as many as 10 million atom bombs, the energy from 10 million atom bombs, that's how much heat you have to remove. Because the heat you have to remove is about the same heat is contained as in 10 million atom bombs. And so you do that in a couple of months. And then in the summer, you're melting this back up, and you have to give that much heat to melt all that ice. So nature moves a tremendous amount of heat back and forth. Okay? And that's just one little lake. Okay. All right, now we'll talk about heat transfer, a different topic. Okay, so I'm going to pause here for a second and let you guys ask questions if you have any. Okay.